The title of my presentation is Deep Learning-based borescope image processing for aero-engine blade in-situ damage detection. Aero-engine operation safety plays an increasing role in the lives of people, the reliability of air transportation, and the academic benefits of airlines. As an important part of aero-engines, the main function of the blades is to compress the air entering the engines and produce a lot of thrust. In the working process of aero-engine, the blades are subjected to wear force, and they are also impacted by foreign objects. Accidents caused by blade damage seriously threaten aero-engine operation safely. Hence, it is necessary to check blades regularly to ensure their safety and reliability. In the last few years, many non-destructive testing technologies (NDT) have been applied for blade damage detection, such as eddy current testing, magnetic particle testing, acoustic emission testing, and so on. However, damage detection of aero-engine blade requires fast, accurate, and convenient methods for in-situ detection, while aero-engine maintains its integrity and the blade are not removed or treated. Compared with other NDT methods, borescope inception is more convenient, and the inspector can visually observe the state of the blade. Therefore, the in-situ blade detection mainly depends on borescope inception, a vision-based NDT method to examine the internal structure of aero-engine, such as blades by industrial borescope. The existing intelligent methods are classified into three categories: image classification-based methods, object detection-based methods, and semantic segmentation-based methods. The methods still suffer the following limitations. Most networks ignore the important influence of shallow texture features on damage classification and localization. Excessive gradient results from hard samples makes the model pay more attention to hard samples and harm the training process, and the performance of the network is unsatisfactory. The basic network of the proposed method is mask RCN, which has been widely used in the tests of object detection and instance segmentation. It consists of the backbone network, the region purpose network, ROI-align, and the multi-head network. Backbone is the most important part of the network. It is used to extract features, mine damage information, and serve downstream tasks. To efficiently generate candidate boxes, a region purpose network is designed. There are many redefined anchors with different sizes and ratios on each pixel in region purpose network to classify them as foreground or background and adjust candidate boxes by bounding box regression. ROI-align process all regions of interest to a uniform size. The multi-head network is used for damage mode classification, damage localization, and damage area segmentation. The enhanced mask RCN network with three functions of damage mode classification, damage localization, and damage area segmentation is constructed. It is suitable to become the basic network. The TFNet is designed to give more attention to the shallow texture information, which reflects the types of blade damage and facilitates the localization and segmentation of the damage. Meanwhile, the information transmission path is shortened by the deep and shallow layer feature fusion module. BL is introduced into the network to improve the accuracy of damage detection by adjusting the gradient and loss of easy samples to achieve a balance between coarse grade and fine grade localization. In this network, the deep and shallow layer feature fusion module and the bottom-up shallow layers feature enhancement module are built to fuse feature maps of different layers that contain different information. The bottom-up shallow layer feature enhancement module is built based on the deep and shallow layer feature fusion module to further explore and utilize the shallow layer features. The multitask loss function is commonly used in the mask assay to solve the problem of classification, localization, and segmentation. To solve the problem of the imbalance between the hard samples and the easy samples, we use BL as a localization loss function. BL replaces the regional localization objective function. The performance of damage localization and segmentation is improved by adjusting the gradient and loss of easy samples to achieve a balance between coarse grade and fine grade localization. There are 3,000 images and 5 damage categories, including crack, broken board, overheated, and nick. The simulated blade images are taken by the digital camera, and some images are added with noise. We hope that the proposed method not only performs well on simulated dataset, but also has excellent results on real engineering dataset. To this end, we carry out field borescope inception to collect borescope images. Then we construct a real blade. The dataset consists of 131 images that come from aero-engine and gas turbines. Consistent with our view, shallow layer features focus on the texture information in the image. The shallow layer of network extracts the contour of the whole blade, and the damages are also noted. For the deep layer feature, the feature map pays more attention to the locations of crack and broken. The deep layer feature weakens the global information and pays attention to damage information. In addition, compared with the powerful baseline, our method obtains satisfactory performance in the used metrics. The proposed method shows excellent results in blade damage classification, localization, and segmentation. Our model can identify damage and has higher confidence than baseline on simulated blade and real blade datasets. To verify the gain of two insights for the localization and segmentation of damaged blades, ablation experiments are conducted according to the result with a best hyperparameter setting. The results are better than the baseline in different thresholds. We also discussed the impact of BL at different stages of the network. The results show that the use of BL in both the region purpose network and the classification regression network can improve the MAP. The use of BL in region purpose network can obtain more accurate ROIs. We summarize the advantages of our method from both industrial and academic perspectives. Compared with the traditional borescope inspection technology, our method involves blade damage detection with intelligence. The proposed method is suitable for damage detection due to more attention to textual information, and it is applicable to the situation requiring high localization accuracy. We list some expectations for further research. Massive data requirement. The idea of unsupervised learning and self-supervised learning bring hope to damage detection under data scarcity, cross-domain detection. Fine-tuning and meta-learning are two methods to alleviate this problem. Open-site detection to model real scenarios closely. Models need to update themselves and classify these samples correctly when the label of unknown is available. In this work, a deep learning-based borescope image processing method is proposed for aero-engine blade in-situ intelligent damage detection to effectively fuse shallow features and improve detection accuracy. We design a TF-net to pay more attention to shallow textual information to make the high-quality detection boxes have higher accuracy. BL is introduced to balance coarse grid and fine grid localization by adjusting the gradient and loss of easy samples. Extensive experiments are conducted on the simulated and real aero-engine damaged blade datasets to verify the effectiveness and progressiveness of our method. We hope that the proposed method can bring enlightening thinking to the research of aero-engine blade intelligent damage detection. Thank you.